3 of CNIT 125, and this is going to take several lectures because it's a big chapter. We did a little bit of it last time. We'll do another 3 Kahoots worth for the next 3 classes, and your presentations are coming up. Next week we'll do the early ones, and the week after, most people, I guess, will be doing their presentations, so I haven't planned to do a lecture that day. If there aren't enough presentations, I might do some more chapter 3 then, but we'll be fine if I just do 3 batches, 3 Kahoots worth each of these 3 days. So that's the plan. So let's pick up here. We talked about these models, the Biba and Bell model and such, and now we're down to some more models. So the information flow model limits how information flows, and that Bell, Padula, and Biba are this, so they limit things like no write up and no read down, as we talked about last time. And the Chinese wall model is, of course, something that a lawyer, you can have a law group that represents opposite sides or related sides in different parties, and they have a Chinese wall within the company where the lawyers working on one case are not allowed to communicate with the lawyers working on another case. That's the idea. So that's another model of controlling how information flows. And non-interference is a property you would like in any computer system. You would like it to make sure that data at different security levels remain separate. If this fails, then there is a covert channel. For example, the one that just happened to UB keys. It turned out that UB keys have a side channel. You can measure the time it takes to perform encryption and do something about the secret key. Another thing you can often do is measure the radio waves emitted by the machine doing calculations, or the power consumption, and from those you can deduce a secret key. So this is an example of a covert channel where some low security information, like the power consumption, reveals high security information. That's a failure of non-interference. You would like it to be that all the operations related to top secret do not have any effect on operations at other levels, like secret and unclassified, and if they do, then you've got a covert channel, all right, or a side channel. Anyway, just taking a look, no new comments in the Kahoots, or in the Twitch. And then there's the take-grant model, where you have rules to take, grant, create, and remove, and you get a complex model of relationships. So Alice can take or remove privileges to secret, because I guess she's the owner of the secret documents. She can grant privileges to Carol, but Bob can take Alice's privileges, and that's the point. Evidently, Bob is like Alice's supervisor. He can take away Alice's privileges. Alice is the owner of this, and so on. That's the idea. You work by taking and granting permissions. Then there's the access control matrix, which is pretty much what Linux and Windows machines and the Mac use, desktop machines. They have user access permissions. Users can have read, write, or execute permissions on things. That's the Linux model, and in Windows it's a few more, like full control, read, write, and so on. 6 levels of control is the way you typically express it, although at the binary level it's actually 14 granular permissions. And there's the Graham-Denning model that has subjects, objects, and rules for things like transfer access, grant or delete access, read, create, or destroy object, create subject, or destroy subject. So as you can see, just like all those compliance frameworks, these are many things that pretty much do the same thing. They give you a set of permissions you could use to control your computer system and limit who can do what on it. The HRU model is the same, but treats subjects and objects as the same, and therefore has just 6 operations: create object or subject, destroy object or subject, enter write into access matrix, and delete write from access matrix. All different ways of doing the same thing. Most anyone can pass a background check. Yep, that's right. All right. Anyway, all right, so the mode of operation determines more about how your system works, and there are 4 basic modes of operation: dedicated, system high, compartmented, and multi-level, and these are from a DoD directive from the 80s. Dedicated is the most secure and the most expensive. Your system contains only objects of one classification level. So if you have top secret data, it sits on your top secret computer, and you don't use any other classification on that computer. And this is why for a while some people at DoD had 7 computers on their desk, because you just had to have a separate system for every level of security. And of course, that would seem to be the most secure. You have a bit of air gap between the different systems, but it's the least convenient and most expensive. System high is where the system contains objects of mixed labels, but any person using it has to be cleared up to the highest object. So that would be a way to make it a little less confusing. So your person cleared up to top secret would have all the data on one machine. They wouldn't need to have separate machines for the lower levels of security. And then compartmented is horizontal security, where even all subjects accessing the system have to have necessary clearance, which is vertical, secret or top secret, but they don't have formal access approval or need to know for all information on the system, so they're placed in compartments, and they then have technical controls to limit you into your compartmented information. And this is how you get SCIFs, sensitive compartmented information facilities. It's the same issue. Compartmenting is a horizontal control, or even though you have top secret clearance, you do not have a need to know for certain top secret topics, so you don't have access to all top secret topics, just ones in the compartment that you're authorized to enter. All right. And multi-level is where you store objects of different sensitivity labels and have subjects of different clearances all working on the same machine. So there has to be a reference monitor controlling access. And so if a top secret subject tries to access a top secret object, they get in. But if a secret subject tries to attempt a top secret access is denied. And this is what we have in Windows, right? You can have a domain controller and groups, and you can have different groups, complicated setups where administrators can go here and executives can go there and sales can go there and customers can go there, and they all have different permissions, and you trust the computer to limit all that. So even though all that data is available on the same system, the computer's operating system has its reference monitor, which controls the access and makes sure that people only see what they're supposed to see. And it's risky. It often fails. People make mistakes. Two places that it's really, really commonly broken are the cloud. Currently, there are appalling statistics about the number of users, accounts, and permissions on cloud systems. It's far more than there should be, and they aren't typically deployed correctly in modern companies. And also I see in APIs. APIs very frequently have actions that are allowed without proving sufficient authorization first. So then you evaluate these things. TCSec was the Orange Book developed by DoD in the 1980s. That was the original one, Trusted Computer System Evaluation Criteria, that determined these terms we talked about before, like the reference monitor. And then ITSec and Common Criteria are international models that came later. So this was the Orange Book, developed in 1983, part of the NIST with an NSA, and it rates security from A to D. And like at a college, A is the best and D is the least. So D is minimal protection, where you don't really have much of a formal process at all. And C is discretionary control. This discretionary access control is what you have as a home machine. You have a machine, you log in, and you can decide to share your files with other people or not to share them at your discretion. And you can also choose to keep them private. It's up to you. You're the owner of the machine, the owner of the data, and you can decide at your discretion what to share. Then there's mandatory protection, which would mean that you have some kind of authority over you that assigns things like sensitivity labels and has to control these things. And then there's verified protection, the highest level, where you have a closed loop of security. That's the way it always is, so that you measure the success of your security system and constantly improve it. That's the idea. Then there's the Red Book, which was the Trusted Network System, which is the same concepts for network systems. And ITSec from Europe separated functionality and assurance. So functionality is how well it works, and assurance is effectiveness and correctness of the security of a system. So that's reasonable. And therefore it had E0 to E6, which is inadequate to E6, and basically it can be mapped across. The E0 is a D, and the high level, like E6, is an A1. And there are other ones here, but as you expect, it amounts to pretty much the same thing in general terms. Just checking. Okay, nothing new in the chat. All right, and then there's the International Common Criteria that is supposed to replace both of them, and it determines the target of evaluation. Pushing an L here. There. And then a security target, which defines what you're trying to accomplish. And then you have a protection profile, which specifies your requirements and objectives, and then an evaluation assurance level, which explains how well you have tested it. And so you end up with these levels. Functionally tested means it does what it should. Structurally tested, methodically tested, designed and reviewed. and formally verified, designed, viewed, and tested. Very, very similar, where you have something that just works at its main function, and then more and more levels of careful security reviews and controls until you get to the highest level. This, I think, is the origin of what I've heard many times, that at the Department of Defense they pay $800 for a hammer, because everything they buy at these high securities has to have all this paperwork and management going on to reach these high levels. Anyway, let's try a Kahoot. I've got to log into them, I think. All right. And it might not be in my favorites yet. It's not. Okay, I got to go here. 25. I need 3B. We're going to need B, C, and D today, and there they are. Good. All right. People in Twitch. I'll wait a little bit longer, see if any more are coming. All right. Aha. All right. Till the end of the song, then. All right. So what feature prevents a covert channel? Non-interference is also called a side channel. It means information is leaking out from your high secure areas through something you didn't intend, like the radio emitted by the processor. All right, what operation mode enforces an air gap between each security level? Dedicated, not compartmented, but dedicated. You have a dedicated set of hardware for each security level, air-gappedly separated from the others. All right, what operation mode uses a reference monitor to control access? That's multi-level. You have multiple levels of users and multiple levels of objects all in the same system, and you trust the computer to sort it out. It's much more convenient, so everybody uses it at all these corporations, but of course it tends to have failures. And the only exception I know to this is cryptocurrency companies that often claim that they have an air-gapped wallet for their reserve of money. And yet there are several cases where they successfully hacked that thing, so it wasn't really air-gapped as well as it should have been. All right, so what TC-SEC level does your home laptop fall under? Let me go back to the slides, talk about that. You go back to TC-SEC, which is here. Okay, so C is where you have discretionary access control, which is what you have when you have an owner. Now, an MS-DOS laptop would be D, where there isn't even an ownership or anything. Anyway, all right, so it's a C. All right. And what's the modern international standard security evaluation method? Common criteria. That's the new model to replace all the others. So, all right, so secure system design. Layering is one issue. You break things up into layers, like you have your hardware, then you have kernel and device driver, then the operating system, then applications. And that's why an application can crash without bringing down the operating system, because you have these layers, each operating to some extent independently. And then there's also the principle of abstraction, where you don't have to see the details, so you just open a web page and you see the web page with pictures. You don't see the individual bytes flying around and the IP addresses and all that jazz. That's hidden away, and you see only what is important to you at your level of abstraction. There are security domains. You group objects together with similar security requirements. So kernel mode is the mode of the processor where it has complete access to all the hardware, but user mode is where you're running on top of the kernel. You don't have any access to the kernel, so if your program crashes, it doesn't bring down the computer entirely. So this works by rings. The hardware has 4 rings, but all modern operating systems use only ring 0 and ring 3. Ring 0 is kernel mode with access to all the machine language instructions and can talk directly to all the hardware, and all the device drivers live in ring 0 so they can control how the hardware is used, and everything you launch from the start button to the desktop is in ring 3 user mode, where you can't touch the hardware directly. All you can do is make API calls to the kernel and ask it to please show something on the screen, please read the keyboard, please print something on the printer, and so on. All right. Now that we have virtual machines a lot, they have this new thing called ring -1, which allows virtual guests to operate in ring 0, and you have to turn this on in your BIOS when you buy a new machine with things like names like Intel VT and AMD-V. This is hardware-assisted virtualization, which is required for most modern hypervisors like VMware Fusion, and makes them run. They claim virtual machines can run just as fast as machines installed on the bare metal, although I wonder how true that is, but that is a claim they make. And I'm going to take a look at Twitch. Why is it C and not D? Okay, good, I explained that. All right, good. All right, so, all right, an open system is where the specifications are published so anybody can understand it. IBM did this, so anybody could make an IBM-compatible PC. A closed system is proprietary, and Macs in their earlier versions had no serial numbers on the chips, and they kept everything very proprietary and secret. And then there's secure hardware. So the system unit is the computer case with the internal components. The motherboard is the main circuit board in there with the CPU and RAM. And the computer bus is the communication system between them. So you have the CPU, and it wants to send data to the display, the keyboard, mouse, the RAM, and the hard disk, and those go over buses, which are just lines on a circuit board typically. Then they had North Bridge and South Bridge, where you have North Bridge that's faster to have things like RAM and video memory, and South Bridge for things that can be slower, like the hard disk and the USB. So CPU is the brains of the computer, with the arithmetic logic unit performing mathematical operations, and the control unit that fetches instructions from RAM one by one and sends them to the ALU for processing. So you fetch an instruction, you decode it, you execute it, you write and save the results, and that all happens in one clock cycle, and most instructions take several clock cycles, like 4 or 6. You have interrupts, are signals that something has happened, like an alarm. You must stop what you're doing and deal with this. Something needs to be handled immediately, and there's a lot of interrupts on modern machines. A task is broken up into threads, and each thread can proceed independently. This deals with the fundamental problem of all computing, that you have very fast components like the CPU and very slow components like the keyboard and the hard drive. And so in a normal computer, you spend a lot of time with the fast component waiting for the slow component to give it the data to work on. So they try to prevent this wasted time waiting for slow things as much as possible, and multi-threading is one of the techniques to prevent that. Oh, even if some thread is waiting for something slow, maybe some other thread is not waiting and it can move ahead in the meantime. And the multitasking, all modern computers are multitasking. They can run several programs at once, but actually there's time sharing between them, a few cycles for this one, a few cycles for that one, but to the user it looks like they're all running at once. Multiprocessing is if you have multiple CPUs, which, by the way, most of us do these days, have multiple CPU cores. All right. And you can have a watchdog timer that notices if the system has frozen and reboots the system. I don't think home machines have this, but I know Cisco routers do. Cisco routers run a check heaps process every minute or so, and if they find corruption in the heap, they just restart the machine, throw away the packets in process, and restore to a known good state. All right. So, CISC and RISC. Complex instruction set computers is what Intel's used, with a huge set of machine language instructions, thousands of machine language instructions. ARM uses a smaller set of machine language instructions, therefore presumably implemented more efficiently on the hardware. A very different philosophy. Of course, they both get the same thing done. They're both Turing complete. There's just a different philosophy of how you want to design your chips. And then there's direct and indirect addressing. If I add EAX8, I take the accumulator, EAX, which is a storage register on the same chip as the processor, and it goes from 1 to 9. I add 8 to it. I can do direct address with a square bracket, and now it'll take whatever's in memory location 8, which happens to be a 5, and add that to EAX, getting a 6. And there's indirect address, where I treat EAX as an address and add 8 to that. So now if EAX contains 12, you go to memory location 12 and add 8 to that. So those are various ways. The square brackets mean that whatever's in there should be treated as an address, not as a value. And one process cannot affect another process. Even as soon as you launch a process, the operating system assigns a certain region of memory for that process to use, and no other process is going to use that memory. That's why it's sort of like running in a virtual machine. Each process has its own memory, so it won't interfere with the other processes. And if they need to talk to each other, they have to use a special exception like mutants, where you can write something that can be read by other processes. But typically they're isolated. And so they have virtual memory and object encapsulation and time multiplexing. Generally, each program runs completely independently in its own region of memory, and it gets some CPU cycles every now and then, and they run independently. Now, when a processor starts, it's in real mode, but no process isolation. Any process can write anywhere in RAM because it basically goes through the history of computing. It's a very simple computer. Then after a while in boot up, it switches to protected mode, and so on. It goes through various stages during the early stages of boot up. Virtual memory is using a hard drive to add additional RAM. So even if you have so many programs running that uses up all the RAM, pieces of the memory will be swapped to virtual memory instead, so you can continue to open more programs, even though you can't really fit them all in RAM at once. It means that when you go back to another program that has been swapped out, there'll be a delay while it swaps them back into RAM for it to run. All right, so if a kernel attempts to access memory in swap space, that creates a page fault, and then it swaps that page from disk back to RAM so you can use it. All right. The BIOS is the code in firmware. When you power up the PC, it runs the basic input-output system, and it probes to see what hardware it has. How much RAM do I have? Do I have a hard drive? Do I have a floppy? Have I got a keyboard and a mouse and a display? And if it doesn't find enough critical stuff, it will refuse to boot and say, I can't boot unless I have a keyboard. But that's the point. You might have changed the hardware while it was turned off. So that's the power on self-test. Write once, read many is things like CDR and DVD-R, where you can write it, but you can never change it. Trusted Platform Module, named after the required component in the Orange Book, is a cryptographic coprocessor, and it can perform cryptography and securely store keys. The analogous component in your iPhone is called the secure element, and it contains your credit card numbers and is used to generate transient keys when you use Apple Pay, for example. So that's the game. It can also be used to store things like hash values, so it can verify that your operating system has not been modified. Beat an L there. All right. All right, and data execution prevention is a relatively modern invention. It came out with Windows XP Service Pack 2, I think, so I guess it's maybe 15 years old in common use. You can now put permissions on RAM. You can mark an area of RAM non-executable, and therefore it prevents buffer overflow attacks where you would inject data in a string so it goes into RAM and then execute it like a program. If it's marked non-executable, even if you are able to inject the data, you will not be able to execute it. So it stopped a whole generation of malware that ran on Windows XP. And address space layout randomization is a similar defense. Every program that launched is randomly relocated to a random place in memory, so if an attacker gains the ability to inject addresses, which is a common sort of attack, they don't know what address to inject to reach the code they've injected. They don't know where you are. So it makes it more difficult for an attacker to find the code. And that's why these were both turned on in Vista. I guess it wasn't XP Service Pack 2. I guess it was Vista when they came out. Anyway, all modern versions of Windows have it, and Linux and the Mac. They all have these defenses. The only system I know that, yeah, that's right, they all have them. All right, so let's take a look at Kahoot for 3C. Okay, think of brackets as meaning pointer. Yeah, that's right. We're able to go back to the third example on slide 64. Let me see. Good, let's go back to that. Slide 64 was here. Okay, perhaps you meant this one. Yeah, is that the one? Most likely. Why 11 rather than 15? Yes, because this adds 8 to the memory address EAX. EAX contains 12, and that contains a 3. So when you add 8 to it, it's now 11. That's all. Okay? Yeah, okay. And now all right, so that's good. Now, think of the brackets as meaning pointer. I know the brackets are a pointer. That's right. Address will get 12, then you add 3. No, it gets address 12, and address 12 contains data 3. That's indirect addressing. So EAX is an address, not a value. All right. Good. Hello. You for the 125 class? You coming for 125?
Yes.
Okay. Let me turn on the projector. Good. All right. Didn't know if anybody's going to come physically. All right, but we're set for that. Okay, so what's that?
Since you missed earlier, I haven't made classes, so I've been in the road.
All right, well, I'm glad you're here. So let's, we're down to a Kahoot, I think. Let's see. We are down to 3C. All right. So that's here. 3C. All right. you there'll be videos on the website for whatever you missed. If you want to do this, yeah, you need to get some kind of computing device and go to kahoot.it. Seconds to see who else is coming. Did you get in? Okay, good. I'll wait till the end of the song. All right, so what ring is user mode? Ring 3. 1 and 2 are never used. It's only 0 and 3, and user mode is 3. All right, users can't handle the truth, so the computer lies to them. What is the term describing this situation? That's abstraction. You show them a picture of something like a folder and files, and what's really going on is more complicated, but they don't need to know that. All right, communication channel between components. That's the bus. Good. All right. When I launch Microsoft Word, what have I created? That's a process. Good. All right, and the cryptographic coprocessor. platform module, which creates what the Orange Book calls a trusted platform, so they can sell that computer to the military. It meets the military standards. What? Well, let's take a 10-minute break. I'll pick up at 6. I'm going to stop this recording.